So this is our theorem 4.31. Again, this usual setup, we are in a vector space. That's always our universe, where everything lives in. Then S, a subset. And then it turns out S linearly independent if and only if you make a combination to 0, so if you combine these vectors to 0, the only way of doing it is if all the coefficients are 0. Okay, so instead of showing this, you can show this. So now you can say, what is the advantage of this? Oh, we just saw this before. Keep in mind, this is a 0 vector. This here is in general a linear equation system. So if you can show the linear equation system has only the trivial solution, then the set is linear independent. So for this reason, we like this much better than this. This maybe makes sense, so you cannot combine them, but it's hard to show something like this. This, if our vectors v1, vr are vectors in Rn, it turns out that this is a linear equation system, and we can handle by now linear equation system. So we like this side much better than this side. Even this side explains it better. But for showing something is linear independent, this is the way to go. Okay, so how do we show this equivalency? Turns out it's pretty straightforward once you think about it. So we have to show this implies this and this implies this. And what we do is we show it by contradiction. So we assume it's not true, and then we show, oh, that leads to a contradiction. So proof by contradiction. So let's go from left to right first. So we assume it's linear independent, and then I assume this is not true. So I assume this. Also given is this, then I assume that we can combine it to 0, but not all of them are 0. Not all Ci equal to 0. If they are not all 0, there's at least one which is non-zero. No, otherwise, if they're all 0, then yeah, for sure. So, and now it's terribly complicated which one it is. So without restriction, I can assume number 1 is non-zero, because if it's number 15, I just change 15 and 1. No? We can always change. So without restriction, C1 not equal to 0. Then I take this equation and bring all the other vectors to the other side. So that means C1 V1 is minus C2 V2 minus CR VR. Now I know this guy is not equal to 0, so I can divide the equation by C1, and I get minus C2 divided by C1 V2 up to minus CR divided by C1 VR. And now we see vector V1, because we assume this, otherwise it may be this arbitrary vector, the one which is non-zero. V1 is a linear combination of the other vectors, and that it means S is not linearly independent. Because linear independent means this is impossible, no? But we have actually assumed it's linear independent, so we have a contradiction. So that means this cannot be true, therefore this is true. Yeah. So we have shown if S is linear independent, and if this would not be true, it turns out actually S is linear dependent, and that is our contradiction. So now we go in the other direction. So now this statement is given, we have to show it's linear independent. And we do the same thing again. Assume as not linearly independent. And then we have to show then this cannot be, no? Sorry, this cannot be. We prove now from here to here. Also instead of not linear independent, I can always write linear dependent, but the not shows you a little bit, okay, we do a contradiction proof. No? Okay, if it's not linear independent, then by our definition means one of these vectors can be written as a combination of the others. That is what not linear independent means. And again, without restriction, we can assume that V1 can be written as a combination of the others. If it's V15, same thing. It will not change our proof. So without restriction, we can assume that V1 is a combination of the other vectors like C2, V2, plus C3, V3, plus dot, 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 plus C3, VR. Then I bring this time V1 to the other side. So I subtract V1 on both sides. So here we have the zero vector. It's minus V1 plus C2, V2, plus C3, V3, plus dot, 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 CR, VR. So now we have a combination of the zero vector where one coefficient is not zero. So we can combine the zero with V1 to VR with coefficients. I don't know what these numbers are. I have no clue, but I know for sure one coefficient is non-zero. Therefore, this is not true. So contradiction. Keep in mind when I say this, we assume this is true. Now we have shown if this is not linear independent, then it turns out it's false. So it's a contradiction. So S contradiction, so S is actually linearly independent. Okay, so we have shown this implies this and this implies this. And as I said, this is actually computational much easier to handle than this. But still, also here, the idea is you cannot take the one vector and combine it with the help of the other vectors. Here you have to show you cannot solve the homogeneous system with a non-trivial vector of coefficients. Okay, so this always comes down to showing that a homogeneous system has no solution beside the zero solution. So we go over an example here. So example. Also example 1 is really our calculation example. Example 2 is also very interesting, but it really depends more on results from other areas of mathematics, but still it's important to know. So the question is here, determine if three vectors V1, which is 1, minus 2, 3, V2, 5, 6, negative 1, and V3 equal to 3, 2, 1 are linearly independent in R3, because each vector has 3 components. Sorry, it's always, yeah. Okay, so the question is, can we now find coefficients, not all equal to 0, which make this combination equal to 0? So we need to find what coefficients make C1, V1, plus C2, V2, plus C3, V3 equal to 0. What are the possibilities for C1, C2, and C3? If the only possibility is C1, C2, C3, 0, then they're linear independent. If there's one non-trivial, which means one of the coefficients is non-zero possibility, then they are linearly dependent. Yeah. So the question is, what are the solutions for the coefficients? And again, when we write this down, we see, so this is C1, 1 minus 2, 3, plus C2, 5, 6, negative 1, plus C3, 3, 2, 1, equal to 0, 0, 0. And this obviously is equivalent to the matrix 1, minus 2, 3, 5, 6, negative 1, 3, 2, 1, times C1, C2, C3 equal to 0, 0, 0. And so we have a linear equation system with this matrix A. Let's call this vector X, our unknowns, and this is the zero vector, so it's homogeneous. And to find all possible C1, C2, C3, back in week 1, bring it to reduced row echelon form, and it will tell you everything. Okay, so our old story, we use Gauss-Jordan to bring it to reduced row echelon form to tell us all possible solutions. Okay, sorry, I have to switch now to new paper to write this up. So we have a homogeneous system. We have 1, 5, 3, 0, negative 2, 6, 2, 0, 3, negative 1, 1, 0. And so now it's good. We have already, sorry, I'm just copy it. So it's good. So we have already a 1 up here. So this will be our leading 1. And I make zeros down here. Plus 2 times row 1 minus 3 times row 1. So we get 1, 5, 3, 0. This plus 2 times this plus 2 times this plus 2 times this plus 2 times this. So the right side actually never changes. This minus 3 times this minus 3 times this minus 3 times this, 0. That looks already suspicious. So we do 2 things in 1 step, so I hope that's okay. I divide this equation by 16 and I add row 2. I should do actually in 2 steps, but just make it shorter. So we have 1, 5, 3, 0, 0, 1, 1/2, 0, 0, 0, 0, 0. That tells us already we have 2 leading ones and a 0 row. That means there are non-variables for non-leading ones, so there will be parameters. So we know, also if the question is only, are they linear independent, we are done, because we know there will be parameters. I like to show you later on how this plays out. So I continue actually finding now these solutions. So I make this also into 0, so minus 5 times row 2. So to have reduced row echelon form, 1, 0, 1/2, 0, 0, 1, 1/2, 0, 0, 0, 0, 0. So this is now reduced row echelon form. And again, this was our C1, leading 1, C2, leading 1, C3, non-leading 1. So 3, 3, C3 gets a parameter. So C3, let's say, is equal to T in R. Then C2, I bring it to the other side, is minus 1/2 T. And C1, again, I bring it to the other side, is minus 1/2 T. So the solutions are C1, C2, C3 is equal to T minus T over 2 minus T over 2. And I can also write it again is minus 1/2 minus 1/2, 1. So it turns out the set of all solutions, it's a homogeneous linear equation system. So this is the kernel. Remember, T and R. I should actually write it here also again. It turns out this is the span of the vector -1/2, -1/2, 1. Though this span of this vector is the kernel. And now you can pick any t you like. For example, t, I just make it, the numbers are a little bit nicer. I make t equal to -2. So for example, also t equal to -2, for example. So we get the vector 1, 1, -2. That means 1 times the first vector, which was 1, -2, 3, plus 1 times, what was the second vector? 5, 6, -1, minus 2 times 3, 2, 1, equal to 0, 0, 0. And this now clearly shows that, like here, we can combine the 0 vector with coefficients where not only that they're not all 0, it turns out they're all non-zero. No, for sure that is wrong. So that means it's linearly dependent, no? Because this is not true. It's not that I have to pick 0, 0, 0. I can pick actually 1, 1, -2. No? So therefore, V1, V2, V3 linearly dependent. And coming back to the other definition, for example, like I said, like in the proof, that also means, for example, now conveniently these two coefficients are already 1, so I can bring these to the other side. So I can also write this equation as 1, -2, 3 is minus 5, 6, -1 plus 2 times 3, 2, 1. That means this vector can be written as a combination of the others. That's again our confirmation. If you can do this, you can do this. Means you can use 2 to combine one of the others. Or we can also solve for this or for this in this case. Also, that's a special case because all coefficients are not 0. So again, that confirms that is according to our first definition, the meaning that they are not linear independent. No? Also, again, how would you do the calculation? If you do this calculation and your only solution is a 0 solution, that means linearly independent. If you have a solution which is not the 0 solution, it means linearly dependent. So here you see now that by using this theorem 4.31, we have turned the question of asking, is a set of vectors linearly dependent or independent, at least when we have numerical vectors, into the question of what are the solutions of a homogeneous linear equation system. And that's again something we can approach with the methods of chapter 1. Okay, the next example is actually again something about independence, but it's not connected to linear equation system. This really comes out of something else. I hope you have heard this before in classes like pre-calculus or college algebra, but usually it's not proved, but at least it's a statement which I hope you have seen.